back. We'll be beginning our discussion on a brand new topic, and that is balancing chemical equations. Previously, we learned how to write a chemical formulae for either an ionic compound or covalent compound or transition metal compounds given a name and the rules that go into writing the names, or the other way around, given a name, how to write a chemical formulae. This time around, we're going to put it all together and try to balance a chemical equation. So what's the bigger picture? Now, we've briefly talked about the law of conservation of matter at the start of the course. This law is much more visible and almost inevitable when we talk about balancing chemical equation. Now, let me refresh you what does the law states. It says matter cannot be created or destroyed, it can only be transformed. We'll come back to it in just a second when we actually talk about an equation. So what does the idea of balanced here refer to? Well, this is the way I have defined it. Number or amount of species of an atom in reactants equals to the number or amount of species of that same exact atom in the products. Okay? I've shown a balanced equation. Now you might be wondering, well, we're learning how to balance equation. We'll get back to that in a few minutes. But before that, if you look at a balanced equation, you notice that whatever atom you pick, if the equation is balanced, that the total amount of that atom on the reactant and the products should be equal. Okay? Before that, let's look at a couple more things. I think I've briefly mentioned this somewhere along the way, but let's actually focus. The number that's in front of the molecule is called the coefficient, and the number below the atom is called the subscript. Please do not mix these two. You can only change the coefficient, not the subscript, because the subscript is inherent for that particular molecule. Okay, so I have 4 hydrogens total on the reactant side. How did I get that number? I multiplied the coefficient with the subscript. And I do the same on the product side. I get 4 hydrogens, and I could do that for the other atom like oxygen here, and I would still get 2. That means my equation's balanced. Okay, now if you notice, the hydrogen is part of a hydrogen molecule in the reactant side, and it's part of water on the product side. It's changed its form going from reactants to product, but it's still conserved. Okay, that's what it's saying. Matter cannot be created or destroyed, it can only be transformed. It's transformed into a different form. Now, why did we talk about these two separately in the conjunction of balancing chemical equation? Literature search indicates that there are common misconceptions associated with the idea of balanced when students learn these concepts. Some of them even retain these misconceptions well after they learned the concept. Maybe they truly didn't learn it. Either way, the misconceptions are, the first common one is because the idea of balanced is almost treated as equal in day-to-day life, they assume that the total of reactant should be equal to total of product. So they try very hard to balance the equation where the addition of the coefficients on the reactant side and the product side should be equal, and they end up never getting there because that's not the way it's supposed to be. And then the second thing they do is they change the chemical formula instead of adjusting the coefficients. That is, in one case the copper might be in +2, and the other they may be writing a formula where copper might be in +1. So that sort of thing happens. They try to adjust the formula, and that's not true. And the third is exact opposite of how we define law of conservation in the context of balanced chemical equation. They assume law of conservation, if they even get that far, does not apply to atoms in a chemical formula, and this is exactly opposite of how we defined it. While knowing the misconceptions themselves does not have an immediate impact, but it's good to have these ideas in the back of your mind. Alright, so here are the 6 common reactions under which most chemical reactions can be placed under. We will not be discussing redox reactions under this particular umbrella of balancing chemical equations, simply because it's not just about accounting for atoms, it's also about accounting for electrons. So we'll come back to that at a later point of time during when we learn electrochemistry. So what are these reactions? So let me go put them all. So try not to memorize these, as it's really not the point of this particular information. I'm just trying to show you, when we balance a chemical reaction, those chemical reactions are part of some family of a chemical reaction, and that's simply what I'm trying to establish here. Synthesis, you combine two reactants, produce a product. Decomposition is the opposite of a synthesis. Combustion is classic, you produce carbon dioxide and water as products. There's a fun fact about combustion balancing reactions. If you have odd number of carbons, the problem becomes much more easy to balance. When you have even number of carbons, it's a little tricky, but we'll look into that as we begin to learn these concepts. And then you have single displacement, where one species get displaced and substituted by the other species. And double displacement goes without saying, just as the name sounds, you just switch two species from one molecule to the other, and you end up with two different products. Now, as I mentioned, we will not be learning redox reaction under this particular umbrella of balancing chemical equations. Now, what prior knowledge do I need? Well, we did go into extensive detail up until this point to understand how the periodic table works. So you need to have a fundamental working knowledge of the periodic table, and then given a chemical formula, write chemical name, given chemical name, write chemical formula. Now you might be wondering at this point, hey, if you're going to give me a balance, if you're going to give me an equation that already has molecules with formulas written, why do I have to know 2 and 3? Well, that's where I beg to differ, because I have designed the curriculum in such a way that every concept as it's learned must be incorporated consistently into the next concept. So not only it makes you aware that, yeah, everything I learn is sort of related, but it also helps you review the concepts. As you learn new concept, the whole concept keeps getting reviewed, so you never have to actually prepare for the day before the exam. You've already reviewed everything. So there are three. I've basically classified 3 types. This is not like 3 different types, it's just 3 different ways of learning it. So one, where I give you the formula and have you balance it. Second, I give you the name, you have to write the formulas, and then you have to balance it. The third type is, I give you the formula of the reactants and have you figure out the formula of the products. Now, for this particular type 3, I would choose only double displacement, because the oxidation state of the species does not change. But we'll get to that. I'm just showing you what I'm planning to achieve here. So this way, consistently, you're being pushed to the limits to show how much you've understood about the concepts. So what's the big takeaway here? Well, this is a great way to refresh and review all related prior concepts and get really good at with whatever you've learned so far. So just hang on tight. I'll be back with actual equations so we learn how to balance. So stay put. Welcome back. This will be the very first equation we will learn how to balance. Now, if you remember during my explanation on the various reactions, when it came to combustion, I mentioned if your molecule contains odd number of carbons, then it's much easier to work with it, and that's exactly what I have done. So I've chosen a combustion reaction, and I'll show you how to balance this equation, right? So I'm going to use different colors, so just to make my life easy. So if you notice, I have odd number of carbons. So first, all I'm going to do is just count how many carbons, hydrogens, and oxygens I have on either side of the reaction. So on this side, I have 5 carbons, 12 hydrogens, and 2 oxygens, right? On this side, I have 1 carbon, 3 oxygens, and 2 hydrogens, right? As I mentioned, the rule of thumb, if you would start balancing the carbon and then the hydrogen and then the oxygen, that will be the more easier way to do it. So what I'm going to do is I'm going to start with my carbons. So I have 5 carbons on this side and I have 1 on this side. How do I go from 1 to a 5? Well, if I multiply 1 by a 5, then I'll have 5 carbons, right? So that means I put 5 in front of where the carbon is, right? So you need to understand one thing. Balancing equation is a synchronization act. So when you change one thing, something else gets changed, and you have to keep an account of that. So what have we done here effectively is, as we changed our carbon count, we also changed our oxygen count on the product side. And what did we do? We had 10 plus 1, 11 oxygens now. That's our new oxygen count. So as I said, now we have accounted for carbons. Let's go tackle hydrogens, and then hopefully and the oxygen works out itself. Now we have 12 hydrogens here, and we have 2. So how do we go from a 2 to a 12? Well, we just multiply by 6, so which gives us 12 hydrogens, right? So we put 6 in front of the hydrogen. So now we have effectively canceled out the carbon and the hydrogen tally. And what have we done to the oxygen in the process? Well, we now have 10 plus 6, 16 oxygen total. Now you see how I'm doing the math, right? I'm multiplying the 5 into the subscript on the oxygen, which is 2, which makes it 10. And I multiply the 6 into the oxygen on the water molecule, which gives me 6, and then a total of 16. Now we have 2 here on this side, and we have 16 on the product side. How do we go from a 2 to a 16? If you just simply multiply by an 8, then we get 16 oxygen, right? So we just put 8 here. And if you notice, everything is tallied for. Basically, you're able to cancel it out. That tells me that we have a balanced equation, all right? Now that's very simple. Now I'll come back with a couple more examples, and then I'll give you some problems to practice. Welcome back. The next problem we're going to work on contains a polyatomic ion. At first instant, to many of you, it may seem that the problem is actually very difficult to work with, but that's actually not the case. I'm going to walk you through some tips on how to do this really easy, right? There is one word of caution when you work with polyatomic ions, that is, try to keep them inside the bracket. Okay? Lack of brackets can cause unnecessary problems that could easily be avoided if you actually have a bracket. So what I have done here is, of course, this problem can be solved in more than one ways. I chose to work with the polyatomic ion itself first. So on this side we have this phosphate. We have 2 phosphates. On this side we have 1 phosphate, right? So how do we go from a 1 to a 2? We multiply by a 2. So where do we put the 2? Well, we put it right in front of our sodium, right here, right? So as I said in the previous video, balancing equation is a synchronized act, right? So we have now accounted for the phosphate as 2, right? But we have in the process changed the sodium. And how many sodiums do we have? We have 2 times 3, which is 6 sodiums. And we have 1 sodium here. How do we go from a 1 to a 6? It's very simple. You multiply by 6. So what do? We now have 6 sodiums. So where do we put the 6? Right in front of the sodium. So what have we done in the process? It's easier if you actually keep count of the element to which you've added the 6. So now we have 6 Cl, and then we have 2 Cl's, right? How do we go from a 2 to a 6? Pretty simple, you guessed it. Multiply by 3. So now we have 6 Cl's, right? So what do? We put a 3 right here. Now if you notice, we have 3 calciums, and we have 3 calcium. So everything is tallied for, and you have a balanced equation. Welcome back. We're going to look at the second type of balancing equation. If you remember, when I gave my introduction, I introduced 3 types of balancing equations that we have to learn, and this is type 2. So how do we go about solving a problem like this? Now that's what I mentioned. We have extensively spent time on or figuring out how to use the periodic table. And one aspect of the periodic table is we can use some information from the periodic table to figure out the oxidation state of an element. Now, we know that sodium is in group 1, right? So it has a stable oxidation state of 1. So sodium is 1 plus. And we know chloride from our polyatomic table is Cl1 minus. Right? Let's go to the next step. So we know calcium is in group 2. So it has a stable and a single oxidation state of 2 plus. And phosphate is a polyatomic ion. Now this is the way I request you to write it. Put the 3 minus outside. So I'll show you why that is. And the next thing is, let's go to the other side. Well, if you also remember from my introduction speech that I've chosen a double displacement, so the oxidation state here doesn't change. So sodium here should still have 1 plus. Well, sodium is always 1 plus. And again, we'll write phosphate in 3 minus. And then calcium is 2 plus. And then phosphate is 3 minus as well. Right? Now let's swap the charges. Okay? I would actually write the 3 minus outside. Okay? So, sorry, this should be chloride. Apologize. Cl1 minus. Right? Because that's calcium chloride, not calcium phosphate. So all we have to do now is swap the charges. So because these are exact charges, this turns out to be NaCl. Plus the 2 comes over here, the 3 comes over here, which leads to Ca2, Ca3, PO4 twice. Now this is why I told you it's critical you include the brackets. And then we have the 1 goes over here, the 3 comes over here, so it's Na3PO4. Keep the brackets. Plus the 2 comes over here, the 1 comes over here, so it'll be CaCl2. Now we have our chemical formulae. Now from here it'll be just another balancing equation, but what I really point out is you have to remember the knowledge you learned previously about the periodic table. Now let's go ahead and balance. As I mentioned previously, if you start with the polyatomic ion, it makes life easier. So we have 2 phosphates here, right? And we have 1 here. So if we multiply by 2 here, we will have 2 phosphates. So what do? We put the 2 here. So that makes it now, we have 6 sodiums and we have 1 sodium. How do we go from a 1 to a 6? We just simply multiply by 6. So we now have 6 sodium on this side as well. So we put 6 here. What have we done effectively in the process? We now have 6 Cl and we have only 2 Cls. So we multiply by 3, which would give us a net count of 6 Cls. So we will put a 3 here. Now if you notice, our calcium is tallied. We have 3 calcium on both sides. And that's how you balance this equation. So as I mentioned, we'll come back to type 3 during next class period. But for now, I'll give you a few more practice problems to work with, and then you can practice that and then just ask me any questions during the next class. All right, I'll see you next class.